Jai Hind everyone. My name is Abhishek Gupta and I am working as an assistant professor in mechanical department. Here I taught material science as a subject. Today I will cover one of the complex topics of material science subject, which is actually based on magnetic, dielectric and superconducting materials. So today these are all the topics which we will study, that what are the diamagnetic and paramagnetic materials, what is the ferromagnetism, what is the domain theory, what is the hysteresis curve, and how hard and soft magnetic materials are, then how the dielectric breakdown occurs, and what are the different types of insulating materials which we particularly use for any work, and in the end we will discuss about the ferroelectric materials. So every magnetic material, every magnet have two poles. One is the north pole and another is the south pole. So these two poles combine to form a magnetic dipole. It has always been seen that the magnetic lines of forces starts from north pole and it always goes toward the south pole. So you can see that every magnetic lines of force starts from north pole and coming towards the south pole. The magnetic lines of forces at the exterior ends are going outward, and at the magnetic lines of forces at the south poles are here the lines of forces are in the inward direction. So you can see here also, if we will take two magnets, north pole, south pole, north pole, south pole. So from north pole all the magnetic lines of forces are coming out, and from the south pole all the magnetic lines are entering. Here also from north pole magnetic lines of forces are coming out and going towards the south pole. So one by one we will discuss different types of magnetism. First is the diamagnetism. Diamagnetism is a very weak form of magnetism that is non-permanent and persists only while an external field is being applied. Until and unless no external field has been applied, then this type of property is generally not seen. It is induced by a change in the orbital motion of the electrons due to an applied magnetic field. Generally, every atoms consists of electrons, and these electrons are randomly oriented. When an external field is applied, then it has been seen that due to this external magnetic field, these randomly oriented electrons aligns opposite to that of the direction of the applied magnetic field, and the magnitude of this induced magnetic moment is very extremely small, and this is always in the direction opposite to that of the applied field. That's why the magnetism induced is of the low value. When placed between the poles of a strong electromagnet, diamagnetic materials are attracted towards the region where the field is weak, because the magnetic moment induced is of the very small nature and it is always directed opposite to the direction of applied magnetic field. That's why whenever a diamagnetic material is placed between the strong electromagnet, this diamagnetic material is attracted toward the region of the low magnetic field. So you can see that this is the dipole configuration for a diamagnetic material without external magnetic field and with external magnetic field. When external magnetic field is 0, so you can see that no dipole moment exists, no dipoles exist, and when some external magnetic field has been applied, then the dipoles are induced within the atoms, and these dipoles align opposite to the direction. It can be observed only when other type of magnetism are totally absent, and this form of magnetism in a material is practically of no importance. So coming on to the next type of magnetism, which is known as paramagnetism. For some solid materials, each atom possesses a permanent dipole moment by virtue of incomplete cancellation of electron spin or orbital motion. So always been seen that the electrons are generally in pair, and due to but in this case, each atom possesses a permanent dipole moment by virtue of incomplete cancellation of electron spins. That's why, in the absence of external magnetic field, the orientation of these atomic moments are generally random. But when a small piece of material possesses no microscopic magnetization, so these atomic dipoles are free to rotate, and paramagnetism results when they preferentially aligned by rotation with an external magnetic field. So whenever an external magnetic field has been applied to a paramagnetic material, it has been seen that the dipoles, which are actually randomly oriented, align themselves in the direction in which in those directions in which external magnetic field has been applied. So both diamagnetic and paramagnetic materials are considered non-magnetic because they exhibit magnetization only when in the presence of the external magnetic field. So you can see in paramagnetism, when the external magnetic field is zero, so the dipoles are randomly oriented, and when the external magnetic field has been applied in the forward direction, so you can say that all the dipole moments are aligned in the direction of external magnetic field. So next magnetism is known as ferromagnetism. Certain metallic materials possess the permanent magnetic moment in the absence of external magnetic field, and this manifested a very large and permanent magnetization. These are the characteristics of ferromagnetism, and they are displayed by the transition metal like iron, cobalt, nickel, and some rare earth metals like gadolinium. So even in the absence of external magnetic field, these type of materials possesses the permanent magnetic moment. That's why these type of materials are largely used where if we want to use that materials as a magnet. So ferromagnetism, you can see when the external magnetic field is zero, in spite of that also all the dipoles are aligned into a particular directions even in the absence of external magnetic field. And this maximum possible magnetization or the saturation magnetization of a ferromagnetic materials represents the magnetization that results when all the magnetic dipoles in a solid pieces are mutually aligned with the external field. So next materials which possess antiferromagnetism properties are shown like this. So these patterns of magnetic spins with neighboring atoms are generally in opposite directions. They are equal in magnitude, but the directions adjacent to each other are generally opposite. That's why this antiferromagnetism is exhibited at a very low temperature, and the spin, since they are in opposite nature, they generally cancel out. So that's why it has been seen that as the spins cancel each out other, most of this results in the paramagnetic behavior, but can also show in ferromagnetism behavior. So you can see that this is the ferromagnetism. In ferromagnetic material have two sets of magnetic dipole pointing in opposite direction, and the magnetic moments do not cancel each other out because the dipole moments in one direction is smaller than the other. You can see that the dipole moment here is big and here it is small. That's why ferromagnetism materials shows the property like ferromagnetic material, because it doesn't completely cancel out like in case of antiferromagnetism material. Then coming on to the what is the magnetic domain. Magnetic domain is a region within a magnetic material in which the magnetization is in uniform direction. This means that the individual magnetic moment of the atoms are aligned with one another and they point in the same direction. When cooled below a temperature called the Curie temperature, the magnetization of a piece of ferromagnetic material is spontaneously divided into many small regions called electrodomains called magnetic domains. So whenever the material is cooled below their Curie temperature, ferromagnetic materials magnetization divides into very smaller particles or smaller regions known as the magnetic domain, and the magnetization within each domain points is generally in uniform direction, but the magnetization of different domains may points in different directions. So the magnetic domain structure is responsible for the magnetic behavior of the ferromagnetic materials like iron, nickel, cobalt, and their alloys. So that's why the interactions between these domains and the alignment of the dipole moment in each domains actually defines the magnetic behavior of that particular material. So you can say that there are three domains. One domain is all the dipole moments are aligned here. This is the another domain in which all the dipole moments are aligned here, and this is the another domain in which dipole moments are aligned here. So these three domains actually constitutes the net magnetism in a particular material. So their group of behavior of this magnetic domain causes the material to behave in a certain manner. So you can say this is the domain wall which actually separate one domain to the another domain. So why generally magnetic domains are formed? A piece of magnetic materials such as iron spontaneously divides into separate domains rather than exist in the states with magnetization in the same direction throughout the material in order to minimize the internal energy. So in order to minimize the internal energy, the magnetic materials is like iron spontaneously divides themselves into separate domains. And whenever a large region of ferromagnetic materials with constant magnetization throughout will create a large magnetic field, extending into the space outside itself. This requires a lot of static energy stored in the field. To reduce this energy, the sample can split into domains with the magnetization in the opposite direction in each domain. So you can say that why generally magnetic domains actually form. So you can say a domain which is too big is unstable. This is unstable, and this divides into smaller part. But a small enough domain will be stable and will not split, and this determines the size of the domain created in a material. If this is still unstable, then it will break down like this, and you can see that here direction is above, here direction is below, here direction is above, here direction is below, here direction is rightward, here direction is leftward. So that's why the direction of the dipoles after breaking the particular metal into different parts causes the magnetic dipoles in the opposite direction in order to decrease the energy of that particular material, so that the energy can be less energy. With less energy, the particular metals can be remain in the equilibrium state. So there are various energy involved in the domain growth. First is the exchange energy, crystalline energy, domain wall energy, and the magnetostriction energy. So one point is known as a hysteresis curve we will study. This curve is drawn between the magnetic field strength and the flux density, which is also known as the magnetization. So you can see as the external magnetic field is increasing, the flux density for a particular material is also increasing in this manner. And one point come this point where maximum magnetization for a particular material has been seen. So while reaching at this point, if you want to remove the external magnetic field, then it has been seen that the magnetization stored in the material will not follow the same path while returning to their initial positions. Even if you want to decrease the external magnetic field, it has been seen that the magnetization for the particular material is not following the same path even after decreasing the external magnetic field. So you can see this is the hysteresis curve. Initially, as you go on increasing the external magnetic field, the magnetization is increasing to this point. And when you try to, you will see that after increasing the external magnetic field, this B value is not increasing. So Again, when you start decreasing the external magnetic field, it has been seen that the magnetization curve is following this path. And when the external magnetic field is zero, at that time it has been seen that the particular residual magnetism has been stored by that material, and this is represented by OR, which is known as retentivity. In spite of absence of external magnetic field, some amount of magnetism has been stored in that material, and this a certain amount of external magnetic the magnetism stored in a particular materials represents its retentivity. On reversing the external field direction in negative direction, we can see that now C points come where external magnetic field is in the negative direction, and then at that point one point comes when the magnetism present in the material becomes zero. Then this at this point this is known as coercivity. It means every magnetism inside the material has been gone, vanishes. Even if you will decrease, if you will increase the external magnetic field more towards the negative direction, you will see that the magnetism has been decreased in the negative direction. Then one time came that in spite of decreasing the external magnetic field in the negative direction, this diamagnetism, this magnetization in the material is not increasing in the negative direction. Then again you will start to increase the external magnetic field in the positive direction. Then you will see that this curve will form, and at the end this is the curve which you will receive. So this curve actually shows that the magnetism present inside the material always lags behind the external magnetic field which we have generally apply onto a particular material. That's why this phenomenon is known as hysteresis, and the curve which we generally obtained by applying external magnetic field and remove external magnetic field, and this curve is known as the hysteresis losses. So this the area under this curve actually represents the hysteresis losses. So a hysteresis effect is produced in which the field lags behind the applied H field or decreases at a very lower rate. So there are two types of magnetic material. One is hard magnetic material and another is the soft magnetic materials. So you can see in case of soft magnetic material, this retentivity is generally higher and coercitivity is lower. Whereas in case of hard magnetic material, coercitivity is higher and retentivity is lower. So you can say both ferromagnetism and ferrimagnetic materials are classified as either soft or hard materials on the basis of the hysteresis characteristics. So coming on to the soft magnetic materials are used in the devices that are subjected to alternating magnetic fields and in which energy losses must be low. One familiar example consists of the transformer cores. For this reason, the relative area within the hysteresis loop must be small. If the hysteresis loop is small, that it means that the energy loss is small and it is thin and narrow. Consequently, a soft magnetic materials must have high permeability and a low coercivity, which I have already told you. Due to the less area, its coercivity is less in the x direction. A material possessing these properties may reach its saturation magnetization with relatively low applied field. That is, it is easily magnetized and demagnetized and still has low hysteresis energy losses due to the lower area inside the hysteresis curve. Another magnetic field is known as the magnetic material is the hard magnetic material. Hard magnetic materials are used in the permanent magnets, which must have a high resistance to demagnetization. And in order to demagnetize, you will need high demagnetization in order to demagnetize that material. So in terms of hysteresis behavior, a hard magnetic materials has a very high reminiscence, coercivity, and saturation flux density, as well as low initial permeability and high hysteresis energy losses. So these are some of the characteristics for the hard magnetic material. Coming on to the dielectric behavior. A dielectric material is one that is electrically insulating, that is non-metallic, and exhibits or may be made to exhibit an electrical dipole structure. That is, there is the separation of positive and negative electrically charged entities entities on a molecular or atomic level. As a result of this dipole interaction with electric field, until and unless no external magnetic field has been applied, these positive electrons or protons will align themselves. But as we apply the external magnetic field, then we will see that the positive and negative charges will separate it down, and this changes the dipole moment of that materials, due to which the domain wall changes its shape and size, and due to this there has been seen that its behavior is generally changing. So due to the dipole interaction upon applying some external magnetic field, these dipole interactions causes the diamagnetic materials to be used into a capacitor, because the dielectric materials has the capacity to store the charges. So another term is the dielectric strength. Dielectric strength is the minimum voltage which, when applied to an insulating material, will result in the destruction of its insulating property. If you will give some potential to a dielectric material, a minimum potential to a dielectric material such that its insulating properties are broken down, then at that strength at which the insulating properties of our dielectric materials are, then that strength is known as the dielectric strength. Electrical appliances or apparatus are generally designed to operate within a defined range of voltage. If the operating voltage is increased gradually at some value of voltage, the breakdown of the insulator will happen. That's why the property which actually attributes to such type of breakdown is known as the dielectric strength. Then next is the dielectric loss. The dielectric losses are generally the electrical energy absorbed by the insulating material, which are generally dissipated in the form of heat when the alternating voltage is applied. Then the loss of heat when an external alternating voltage is applied is known as the dielectric loss. Then coming on, next topic is the insulator. As we have already been known that the insulators are the materials which generally retards the flow of electricity. So there are various different types of insulators which are generally used for electrical and electronic components or their assemblies, and some of the insulators are the porcelain, plastic, ceramic and polymer. The materials which have very high resistivity, like which offers a very high resistance to the flow of electric current, and the insulating materials plays an important part in various electrical and electronic circuits. In domestic wiring, insulating materials protect us from shocks and also prevents the leakage currents. That's why every electrical appliances have some plastic or the polymer based protection, which actually allows you to be safe from the electrical appliances even when there are the chances for you to get the shock. So that's why every electrical appliances has been given this protection cover, and this protection cover is generally nothing but the insulator. So these insulating materials offer a wide range of uses in engineering applications. So next we will discuss what are the factors which actually affects the selection of an insulator. Firstly is the operating condition. Before selecting an insulating material for a particular application, the selection should be made on the basis of the operating temperature, what is the pressure, and what is the magnitude of voltage and the current. Then on that basis, generally an insulating material is selected. Then second factor of selection is the easy in shaping. That its shape and size is the most important factor which actually we generally select while selecting any insulator. Then third is the availability of the material, that if this material is easily available or difficult in available. Then fourth one is the cost. Cost is generally an important factor, because if the cost will be high, then it will not be easily possible to use that type of insulator. So coming on to the brief overview of the conductors, insulators and semiconductors. Conductors are those substances through which electric currents can easily flow. like silver, gold, copper, aluminum are generally comes under the conductors, and these conductors have a very large number of free electrons. So these free electrons used to carry charges from one point to another. So the flow of charges is can be possible in case of conductors, and all metals are generally good conductors because in all conductors the electrons are generally free. Then second type is the insulator. These substances are those substances in which electrical current cannot pass through easily, and that's why these substances are known as insulators. And the examples of insulators are glass, mica, dry air, and the bakelite. Then third type of material is the semiconductors. These substances have some these substances resistivity actually lies between the resistivity of the conductor and the insulator. That's why these substances are known as the semiconductors. And the example for semiconductors are generally germanium, silicon, and carbon, etc. Then fourth is the resistivity. Resistivity is the resistance between the two opposite faces of a cube, having each side equal to 1 meter. So this resistivity of a conductor ranges are given. For conductor 10 to power minus 8 to 10 to power minus 3 ohm meter. For insulator 10 to power 10 to 10 to power minus 20 ohm meter. For conductor semiconductors 100 to 1.5 ohm meters. Then the fifth one is the insulation resistance. The resistance generally offered by the flow of current through the material is called the insulation resistance. So there are various factors which actually affects the insulation resistance. First is the temperature. As the temperature of the insulating material rises, its insulation resistance keep on falling. Then second factor is the moisture, that insulation resistance is reduced if the material absorbs moisture. So insulation material should be non-hygroscopic. Third is the applied voltage. Applied voltage also affects the insulation resistance. And fourth is so in order to get the better insulation, the age of that particular material should be small. We should use in a particular time frame. There are various different types of insulating materials, acrylic, ceramic, you will note it down. Then why electrical insulation is required? Electrical insulation, I have already told you, is required in order to avoid you from getting the electric shock or getting the fatal injuries. So for DC voltage, 40 volt is sufficient, and for AC, 60 voltage are considered to be the safe limit in order to use the particular materials. So metals reacts very little resistance to the flow of electric current, and these metals reacts with very little resistance to the flow of electric current, and these are known as the conductor. As we have already previously mentioned, that the materials like asbestos, porcelain, PVC, dry wood reacts with very high resistance to the flow of electrical current, and this is known as the insulator. Then these are the applications for the insulating materials like cables and transmission lines. Then next, coming on to the ferroelectric materials. Ferroelectric materials are those materials which exhibits spontaneous polarizations. Polarization means that it has the ability to polarize even in the absence of the electric field. By converting the direction of the applied electric field, the direction of the polarization of these materials can be inverted or changed. If the material is not under the environment of the external magnetic field, then materials will behave as just like that. If you apply the external magnetic field, it has been seen that the materials, the domains plus minus align themselves according to that. So this property of the atoms which align themselves depending upon the external magnetic field applications, then this phenomenon is known as polarization, and this is also called as the switching. It can also maintain the polarization even once the field is removed. These materials have some similarities like that of the ferromagnetic materials, which reveals permanent magnetic moment. So hysteresis loop is almost same for both the materials, since there are similarities like prefix is same for both the materials. Piezoelectric effect. So you can see that these are the two capacitor plates, and this is the external magnetic field, and this is the battery. The positive terminal is connected to this battery, and negative terminal is connected to this capacitor plate. So the dipole which has been present inside the material you can see nearby positive all the negative electrons will come, and nearby negative all the positive electrons will come. Since here negative is there, then other side will be the positive, and here the positive is there, then other side will be the negative. So in this manner, the ferroelectric materials obtains their shape based upon the application of external magnetic field. So if you will reverse the voltages by connecting the capacitor plate to the negative terminal and connecting the another capacitor plate to the positive terminal, you will see that when an external magnetic field has been applied, you will again see that the negative electrons will attract the positive ions, and these positive ions will attract the negative ions. So these are some of the examples for ferroelectric materials like BaTiO3, triglycerine sulfate, lithium tantalate, etc. And these are the applications for the ferroelectric materials like thermistor, oscillators, non-volatile memory, filter, capacitor, and so on. Thank you, class. For any query, you can mail me at guptaabhishek@akgec.ac.in.